So in this topic, we are going to find out what is the electric potential due to uniformly charged infinite line. Earlier we found the electric field intensity due to the infinite charge distribution line. Here we can see that a line which is uniformly charged. Its line charge density is rho L, and P is a point which is at a distance h from this line charge distributed line. And the electric field intensity has two components, that is horizontal component and vertical component. And vertical component is the net value of the vertical component is 0, and only horizontal component exists. The infinite long conductors, the electric field intensity Ex value, the horizontal component is rho L, which is upon 2 pi epsilon h. Now we are going to use this information to find out what is the potential at that point, that is potential at the point P. Let us assume that a point charge Q is moved from one point R1 to another point R2 in the electric field. So this work done is against the electric field, so the work is always the minus QE and the distance. The distance is dH, because here we use the parameter h for measuring the distance from this conductor to this point P. So for a small distance we can consider it is a dH. So dH is a very small distance which is approximately very close to the value of 0. So we are putting the value of minus because the work is done against the electric field E. This equation we know that because F is E times Q. This is then work done is nothing but the force into the displacement. So the force into the displacement, let us take it as a displacement is dH. So small work done dW. If the force is against the electric field intensity, it becomes minus. So minus EQ dH. If you want to find out what is the work done moving a charged particle from R1 to R2, then we need to integrate this function from R1 to R2. So the W become R1 to R2. Now we can take out this the constant, that is minus Q, and integrating R1 R2 E dH. Now we can substitute the expression of E. So E is rho L, which is upon 2 pi epsilon h. Rho L, which is upon 2 pi epsilon h. So substitute here, integrating R1 to R2 rho L 2 pi epsilon h dH. Now this again become here the integration is with respect to h. So we can take out the remaining parameters, that is minus Q rho L 2 pi epsilon, integrating the function h, so 1 by h dH. See here it is 1 by h. When you integrate this 1 by h with respect to dH, this become natural log. So the W become minus Q rho L 2 pi epsilon natural log of h, and upper and lower limits are R1 and R2. this W become minus Q rho L 2 pi epsilon natural log of R2 by R1, because if you expand this one, this become natural log of R2 minus natural log of R1. This is equal to natural log of R2 by R1. Natural log is nothing but the log, its base is E. Now there is a minus sign here. If you take the minus sign to the natural log, it become Q by rho L 2 pi epsilon. The upper and lower limit will reverse. R1 by R2. This is a work done. Whereas the voltage is, electric potential is work done per unit charge, W by Q. So W we know that this is Q rho L 2 pi epsilon natural log of R1 by R2 by Q. So Q get cancelled. So this final expression become rho L 2 pi epsilon natural log of R1 by R2. So this is the expression of the V. This is the expression of the electric potential between two coordinates when they are in the electric field produced by a infinitely long line charge.